All right, so in this lesson, we're going to go over climate change and energy. So feel free to press pause and take a look at this cartoon. I think this is pretty typical of some viewpoints on climate change. I also wanted to point out before we begin, um, I'm recording this video in March of 2017, and this is a tweet from the current president of the United States. We had a cold snap. I'm here on the east coast of the United States. We had a cold snap in late December. Really, really unseasonably cold, like below freezing. Anyway, go ahead and read this and see if you can think of anything that's wrong with this statement. Here's another tweet from him, and this is from October of 2015. So this is really common, whether it's a purposeful or just a lack of awareness. To be honest with this president, I don't know which it is. He may have absolutely no idea even the concept of weather and climate and what makes things cold and keeps them warm. There's a good chance that's the case. He also could be trolling us because he is known to be a pretty big troll, like trolling people, not an actual troll. But this is a really common issue. Whenever we have a cold snap, it's unseasonably cold, whether it's in the summer and we get like a 40-degree day, or it's in the winter and we get this really freezing cold day. People say, aha, see, what's with this global warming stuff? Well, there's hopefully you're already aware that this is an issue. First of all, it's important to point out, and this was a reaction or a response tweet. So if you can see this map shows you the temperature anomaly. This was right at the same time that Trump sent out that tweet. And so you can see this. This is the dark purple and blue means it's colder than normal. The red means it's warmer than normal. Darker red means more extreme hot heat, heat relative to what it should be. So hopefully you can kind of figure out where you are on this map. You can see this really cold spot near the east coast in Canada, basically the eastern half of the United States. But what you should also notice about this map is basically the rest of the world is experiencing at the same time extreme heat waves. Okay, I mean you look up in near the North Pole and in northern Russia. I mean they're almost 10 degrees above normal. We just happen to be around 10 or so degrees below normal. So that's one really, really important point, is that it's a global consideration. It doesn't matter what's going on just here in the eastern United States. It matters what's going on everywhere else in the world. Okay. It's also important to remember that it's climate, not climate change, excuse me, not weather change. So what Trump is referring to is weather. It's cold weather. Climate is the long-term impact. So we'll talk about the difference between weather and climate. So there's a couple of things wrong with this, but another, I think kind of a funny response that someone had was, global warming is fake because it's cold where I am. No one in the world is starving because I have food in my kitchen. Poverty isn't real because I just got paid, and around we go forever. So the point here is that it's not just it's a global phenomenon, and we'll talk about that today. But also it's important to consider that it's not just what the weather is like that day. It's how the weather is long term, which is what climate really means. All right, so the first part here, we're going to go over some energy sources, so the difference between renewable and non-renewable, and sort of how they relate to climate change. We're going to go over a couple of different energy sources here. So first of all, this is a slide from earlier in the class. Hopefully it looks familiar. Not going to go over it all again, but this shows the price of oil over time. So if you remember, we discussed how oil and fossil fuels in general are basically inextricably tied to the development of modern society. Okay, so we have our last 150, 200 years. We've had cheap oil the whole time. We've had relatively cheap coal and then natural gas. Okay, so remember that energy is really important, not just from a climate change perspective, but also energy is really important just in terms of society and society's development in general. Okay. All right. So let's look at a few key questions here. First of all, what's a non-renewable energy source? So you may think, well, it's just something that's non-renewable. Well, there's a little bit more specific definition. There's generally considered not renewable on a human time scale. So what does that mean? That means, around, let's say 20 to 30 years. And most of these, you have the coal, oil, and natural gas. I mean, they take millions of years to form. But where this gets a little bit gray is if you have something that takes maybe 30 or 40 years, like you have a tree, think of like a giant sequoia or something like that, that might take 50, 100 years to grow back. You can't really consider that renewable. Yeah, on a long enough time scale, it'll come back. But the point is, it's not, for practical purposes, it's not really renewable. Okay, so something that comes back pretty quickly. Think a fast-growing tree, or corn, which we use for ethanol. And then of course you have sunlight and wind and everything that comes right back. But that's it sort of has to come back in a really short time scale. Okay. So a fossil fuel, which is a term we've thrown around already, it's technically a fossilized hydrocarbon derived through natural process from organic material. You don't have to have that definition memorized or anything, but it's good to know. But it does tell you what a fossil fuel really means. So let's start breaking it down a little bit. So a hydrocarbon is something that's made primarily of hydrogen and carbon. So if you looked at the molecular makeup of a fossil fuel, it's made primarily of hydrogen and carbon. It's these long chains of hydrogen and carbon. And there's other impurities in there, nitrogen, sulfur, and so forth. But it's primarily made out of hydrocarbon. And we'll get into the how they were derived here in a minute. So first of all, the three main fossil fuels are coal, oil, and natural gas. Okay, so coal, I'm sure you're all familiar with. Black or brown rock, depending on the type of coal that it is. Oil, it's a black, gooey stuff, gooey liquid that we use to make, gasoline and diesel, and other, plastics are made out of oil and so forth. So natural gas is something, it's just a gas, okay? It's in the ground and it forms at the same time as oil, and so we'll get to that in a minute. It's important to know the three main fossil fuels are coal, oil, and natural gas. There's some other fossil fuels, butane, methane, pentane, all these other ones, but the main ones that we use are coal, oil, and natural gas. Okay, so how were fossil fuels formed? If you remember, the hydrocarbons, fossil fuels are hydrocarbons that were formed through natural processes from organic material. Okay, so organic material is something that was recent, is living or recently living. Okay, so fossil fuels, and I'm sure you've learned this at some point in your life, but there's also a video posted, and I think a reading posted on this as well. The quick story is that hundreds of millions of years ago, there were a lot of things swimming in the ocean. Some were shallow seas, open ocean, whatever. I don't like this graphic that much. It's from the Department of Energy, so it's a good source. It's not so much monster worms and giant squid and manta rays and things like that. Most natural gas and oil started out as these little microscopic organisms that called phytoplankton that are floating at the top of the ocean. Okay, so phytoplankton are like little plants that you can't see with your naked eye, and so they're photosynthetic. They exist near the top of the ocean. You could go out in the ocean today, you could go out into any body of water today, and you see phytoplankton. They take in sunlight, and then sunlight and carbon dioxide, and they grow and they release oxygen just like a plant. And so what happens is over time, these things, especially near the surface, they die and sink to the bottom. Then more grow, they die and they sink to the bottom. You end up with these big, thick layers of organic material at the bottom of the sea. Okay, so here's your layer at the bottom of the sea. And when those get buried, so this is over the course of millions of years, as erosion occurs and these get buried, what happens is over enough time, millions of years, these dead plants and animals are undergo metamorphosis. Okay, so they're buried under a bunch of rock. Okay, and then so it's all the heat and pressure turns them into oil and gas. That's the quick story. Okay, so the question is, where is the oil and gas? So it's under the ground. We know that. Is it in like a kind of this underground pool or whatever? Is it kind of like these lakes of oil and gas that are sort of trapped under the ground? The fact is that the oil and gas exist inside of rocks. So this is a sandstone, an oil-bearing sandstone. Okay. And so if you could actually go use a microscope and look inside the stone itself, you would see, so sandstone is a really common stone. There's a lot of sandstone here on the East Coast. You see it all the time. And it's made of it's sandstone, so it's sand grains. So you remember the sand and silt part. So what happened when the sandstone was formed is it was formed when it buried this organic material, and as it was forming, okay, so the sand became rock, and then the plant animal remains became oil and natural gas. When it was forming, it ended up trapping. So this is a microscopic view of the rock itself, and so these are the sand grains here, and you can see there's little pieces of or little bits of oil actually inside of the rock, inside of the pore spaces of the rock. And so this is actually basically filled with oil and possibly gas. And so the good thing about sandstone is there's these pore spaces in there, and if you notice, these spaces are pretty well connected, so the oil can actually flow through the sandstone if given the right conditions. And so what happens when you have a pocket of oil and gas, and by the way, oil and natural gas form at the same time. When you find oil, you're going to find gas. When you find gas, you're going to find oil. And so what happens is you have this porous rock like a sandstone under high pressure, and the oil and natural gas actually start migrating upward because the pressure decreases as you get higher, and so it slowly migrates its way up. And when you end up with this pocket is when you have a non-porous rock like a clay or a siltstone or whatever. So the gas and oil slowly rise up and they hit this cap rock and they can't go any further, and it ends up saturating all the pore spaces. So you'd have a rock like this that's completely saturated with oil and natural gas, and then in order to access it, you drill down, you find that pocket, and that's how you get your oil and natural gas out. Okay? And so that's how it's pretty incredible that these the world extracts about 100 million barrels of oil every year, and it's pretty much all in rock. The newer methods are hydraulic fracturing, which we'll get to later, and fracking. That's mostly in shales, and so there's not a lot of connection between the pockets inside of a shale, and that's where you actually take and you have to break open the shale in order to extract the oil and natural gas. Okay, so that's how they're formed, that's how we get it. Okay, so let me show this short video about oil and gas formation.
What drives our cars, buses, and planes? Powers our electricity and allows us to cook our food and heat our water. Most of today's energy needs are met by fossil fuels, like coal, oil, and gas. These unique, high-energy fuels are non-renewable resources that took millions of years to form. About 2 billion years ago, marine organisms like algae and microscopic animals and plants died and settled on the ocean floor. Beneath other sediments in the ocean, and in the absence of oxygen, these fossils changed into a substance called kerogen. Under heat and pressure, kerogen gradually changes into oil or gas. The whole process usually takes at least 1 million years. At the molecular level, oil and gas are hydrocarbons made up of hydrogen and carbon atoms. The constant pressure and movement of the Earth's crust squeezes oil and gas through the pores or spaces within rocks. Some oil and gas reaches the Earth's surface and seeps out naturally into land or water. Often it is trapped beneath the surface by impermeable layers or rock structures, like faults and folds. Within the crust, oil or gas deposits build up and form reservoirs. Reservoirs are like vast sponges filled with oil and gas. They can be as large as a city. To find oil and gas deposits, geologists use a number of different survey techniques, including seismic surveys, gravitational surveys, and geological mapping. Seismic surveys use reflected sound waves to produce a 3D view of the Earth's interior. New technologies, such as four-dimensional projections and sophisticated graphic renderings of rock structures, are improving the way we find conventional oil and gas deposits. Energy resources that are currently difficult or expensive to extract are called unconventional oil and gas.
Just a quick note here. You see how it says hydraulic fracturing? So that's the unconventional sources. It's not, that's where you actually have to crack the rock open.
In a world with limited energy resources, people are looking at more efficient ways of tapping into unconventional oil and gas, or at alternative and renewable sources of energy from biofuels or the sun. What do you think will be the energy sources of the future?
Okay, so let's get back to the presentation here. So that, I think, does a really good job of quickly explaining how oil and natural gas was formed. Okay, now on to coal. So coal is formed in a very similar way, except coal forms in swampy areas. Okay, so remember, oil and natural gas in these oceans or shallow seas. So coal is very similar. If you've ever walked in a swamp or a swampy area, you probably know that it's sort of like sticky and mucky at the bottom. Well, that sticky stuff at the bottom is dead organic material. And so same thing with, similar to oil and natural gas, you have these big piles of organic material that sinks down to the bottom of the bog. And so then that gets buried. Eventually that forms into something called peat, P-E-A-T. It's like a sponge almost. And then over enough time, that turns into a lighter brown coal. It's called lignite. And then that sort of classic black coal that you see is anthracite coal. So it's actually a process. So where oil and natural gas is sort of like it's oil and gas or it's not. Whereas coal has there's actually different grades of coal. Okay, so there's a video here. I do suggest you click on it. I don't want to spend the time to do it, but it gives you a good idea of how coal, one way that coal is actually mined. Okay, so why are we talking about fossil fuels? A, remember, they're really important because we use a lot of them. B, fossil fuels, in the context of today's discussion, they emit CO2. Okay, and so how do they emit CO2? It's just because we burn them. We burn them to extract the energy out of it. If you look at the combustion equation, again, you don't need to know this, but this is your basic hydrocarbon fuel source, and you probably know in order to start a fire, you need enough oxygen, you need enough heat, and you need your fuel source. So when a hydrocarbon like oil, natural gas, and coal burns, the main byproducts are carbon dioxide, water vapor, and then more heat. So this CO2 is the reason why we're so concerned with fossil fuels with regards to climate change and greenhouse gases. Carbon dioxide is the main greenhouse gas. Okay, so we burn it, and it causes CO2. There's nothing you can do. I mean, it's gonna end up causing CO2. Now you can sometimes capture it, but that's another story. All right, so those are all non-renewables. Those are our fossil fuels. Now nuclear energy is also non-renewable. So nuclear energy comes from the stuff that we use is mostly from uranium-235. This is what a uranium deposit normally looks like. So it's just yellowish rocks. Uranium's all over the place. There's probably uranium outside of wherever you are right now. There's some trace amount of uranium in the soil. But what you need is a high enough concentration, and then you actually refine it. It's something called yellow cake, and this is the stuff that they put in the nuclear power plants. So here's the thing with fossil fuels, we burn them to get the heat out. Really what we're trying to do is get the heat to spin a generator to generate electricity, or sometimes just use the heat itself. With nuclear, we're trying to get the heat out of this. In order to do that, it does something called fission, which is splitting of the atom. You're probably familiar with this process, at least vaguely. So with nuclear fission, you actually fire a neutron inside these nuclear reactors. It hits the uranium. It splits the uranium atom. So the uranium releases energy, releases heat energy, but it also releases more neutrons. And so then these neutrons hit more uranium atoms, those atoms split, they release more neutrons, so it ends up being this out of control chain reaction, which is why if you've ever seen, actual footage or movie footage or whatever of a nuclear explosion, it's this huge mushroom cloud, really out of control energy release, because it's this huge chain reaction. Just these atoms split, and then they split more atoms, they split more atoms, they split more atoms, on and on until it's all gone. And so it's at the same time releasing all this heat energy. And inside of a nuclear reactor, we actually capture that heat energy in order to spin a generator to generate electricity. But here's the really important thing about nuclear. It's not renewable, but we don't burn it, so there's no CO2 emitted. So there is zero CO2 emitted when this fission process. It's just heat, and then of course we have all the nuclear waste, which is a whole other story. And this is a huge debate in sustainability circles today. Should we use more nuclear because there's no carbon dioxide emitted? The big problem with nuclear is there's nuclear waste that is radioactive for hundreds of thousands of years, and right now we don't have anything to do with that waste. Okay, so that's the short story. Fossil fuels are non-renewable. They emit CO2 when you burn them. Nuclear is also non-renewable, but it's considered a carbon-free source. It does not emit CO2 because it's not burned. It undergoes fission. Okay, so a non-renewable energy source is not renewable on a human timescale. So a renewable energy source is renewable on a human timescale. Okay, so either some of them are renew themselves right away, others take a little bit of time. So go ahead and press pause if you'd like. Think about some renewable energy sources. The main ones that we use in the world today are solar, which is just sunlight converted directly to electricity. Wind, which is you're spinning a turbine which spins a generator to generate electricity. Hydroelectric, which uses moving water to spin a turbine, generate electricity. And then biomass, which is anything that was living or recently living. So it could be wood pellets, corn. We can use algae. You can use animal dung. There's all kinds of things that you can use for biomass. So those are the four main ones today. There are also smaller ones, geothermal, wave and tidal. These ones aren't really used very often. So the key to renewable energy is that A, it's renewable. So it's something that if we use most of them, like solar, wind, and hydro, solar and wind we can use as much as we want. We're not worried about running out of solar, sunlight, and wind. Hydro, we only have a limited amount, but there is still more hydro potential in the world. Biomass is a little tricky. It's renewable, but remember, it has to, we've talked about this before with Herman Daly and the steady state economy and everything. If we're using trees, for example, we can't harvest them any faster than they regrow. Otherwise, it's not technically renewable, okay? So not all renewable energy sources are created equal. But we can keep using them over and over as long as we use them at the right rate. Okay, and so the other two important terms I want you to distinguish between are carbon-free and carbon-neutral. So a carbon-free energy source is one that emits no CO2 when it's generating energy. So solar, wind, hydro, you could take a little solar panel, go outside right now. If there's any sunlight at all, it'll generate a little electricity and nothing else. A little bit of extra heat, but no emissions, no carbon dioxide, nothing. Wind, same thing, no emissions whatsoever. Hydro, also no emissions whatsoever. Now, that's carbon-free, so there's no CO2 emitted. Nuclear is also a carbon-free energy source. No CO2 is emitted when it's generating energy. Carbon-neutral, on the other hand, it's important to remember that, so biomass is considered carbon-neutral. If you burn wood, okay, you're going to emit CO2. But here's the thing, the CO2 that you emit when you burn this wood, if you think about where the wood came from, if you have a tree, the tree pulls CO2 from the atmosphere, okay, stores it as biomass, and then when you burn it, you just release it back out. So overall, it's actually balanced. So any biomass that you burn, as long as it's something that's recently alive, you're basically taking CO2, taking it out of the atmosphere and dumping it right back in, and so that's the neutral part of it. It doesn't have any impact on the overall concentration of CO2 in the atmosphere. Whereas these carbon-free energy sources, there's no carbon implications whatsoever. Okay. So just to give you a quick snapshot of the energy being used in the world, this is data through 2013, and then the rest is a projection. So you notice here's basically your oil, here's your coal, here's your natural gas. So there's, I think, a couple of really important things to notice here. One, the overall energy use. This is 1990 to projected to 2040. Okay, so you can see the overall energy use in the world is going to increase. There's, barring any major catastrophe, this is going to happen. You have countries that are using more and more energy. Your China's, your India's of the world, so forth. So that's one important trend to keep in mind. The other thing, if you think of these So if you go from here to here, so this line here, those are all fossil fuels. So you notice that fossil fuels are far and away the biggest source of energy in the world, and they're going to continue to be. Okay, so fossil fuels are really important. Again, to our earlier discussion, fossil fuels are absolutely essential. But then, per what we just talked about, there are some implications for fossil fuel use as well. And also, even though renewables, you can see the line is getting a little bit thicker with renewables, it's still a minor energy source overall. Nuclear, we have kind of, there's a little more nuclear, but it's not going to be that much more. So this just gives you a little snapshot of the types of energy we're using in the world. And so in the next lesson, we're going to go over more of the climate change specific issues.